Okay, yeah. Well, an enumeration is essentially a sequence of values, right? And by functional enumeration, I mean enumerations where we can do this. So we index to the 10 to the power of 100 position in this sequence of this algebraic data type, and we immediately get the value back. So index is an overloaded bijective function from the natural numbers to this enumerated type. We know that such functions exist. It's kind of the definition of an enumerable set that such a function exists. But what we contribute is a way of efficiently and simply compute these functions. And also, we want to be able to do this automatically. So we don't want to have to tell it, how to build an enumeration for this type. We just give it sort of definition of a type, and it should be able to do that automatically. So we have this fancy library on Haskell, but it's really so simple. So the code I will show you in these slides is actually a self-contained implementation of the core of this, and hopefully it won't make your eyes bleed too badly. Yeah, so what we use this for is property-based testing, essentially. I mean, there could be other applications as well. I'm sure you can imagine where this could be useful. So, enumerations of lists of booleans could look something like this. So the kind of sequences we build are ordered by size under some definition of size. We start with smaller values and move on to larger. Of course, there's also some kind of internal ordering of values of the same size, but we don't care so much about exactly which ordering that is. And equivalently, we can define this in terms of the index function, of course. 0 maps to empty list, 1 maps to false, etc. 10 to the power of 100 maps to something. So nothing controversial here, I hope. So, more generally, we want to partition sets. And a partition is a sequence of sequences, where each inner sequence contains values of a particular size. So here we have fixed the definition of size to being the number of constructors in a value. There are no lists with 0 constructors, and there is only the empty list with 1 constructor, and no lists with 2 constructors, because we actually need 3 constructors to build a singleton. Yeah, but if we just concatenate these inner sequences, we get the sequence that I showed you on the last slide, the kind of flat enumeration. So partitioning is a bit more fine-grained, because we can do stuff like select all the values of a particular size, or randomly select a few values of a particular size. And one thing to note here is, although this list is infinite, typically, each of these inner lists are finite. Because for any algebraic data type, we have, of course, a finite number of values built from any number of constructors. So then we want maybe a data type for finite sequences with fast indexing. And of course, there are already a few of those in Haskell, so could we use one of those? Well, so what we want to represent in this could be stuff like all the absolute syntax trees in Haskell with 100 constructors. And there are billions of such values, but we don't want to use terabytes of memory to represent them. So we need to make something slightly more involved here. So I came up with this type for finite sequences, and in light of inspiration, I named it finite. So each finite sequence has a cardinality, which is just the length of the sequence, and the indexing function, which is what we're aiming at here. So maybe the easiest way to specify how this works is just by isomorphism with finite lists. So as I said, cardinality is just the length, and this indexing function is just list indexing. And I will kind of use this when I explain the operations that we have on this, that we need on this in order to do what we want to do, enumerate algebraic facts. So we have empty and singleton, simple enough, and they follow quite naturally from this isomorphism. Map is also simple. As you may note here, we will recompute f if we index to the same value twice. And that's a feature, not a bug. It's one of the things that makes this practical memory-wise, right? If we know how to construct the value, we will try not to keep the actual value in memory. So sum is kind of the dual append for lists. The cardinality is just the sum of the cardinalities of the operands. And indexing is also simple if we consider this isomorphism with finite lists. Because if we index in two appended lists, then it's just indexing into the first list if the element is there. And if it is not, then we kind of trudge through this list, decreasing the index as we go, and then we end up indexing in the second list. So we just skip the trudging part here, and we jump directly to indexing in the second list, of course. Since we can compare to the cardinality, we know which of the operand it's in. So it's worth noting here that this operation uses only constant memory, but it can kind of linearly increase the number of values, which is not spectacular, but worth noting. For product, naturally we get the new cardinality by just multiplying. And accordingly, for indexing, we can break down the index into index for the components of the pair using integer division with the cardinality of one of the operands. Which operand we use affects the ordering, but if we use the right operand, as I do here, then we get this isomorphism with this comprehension. So you can think of this as just breaking a linear index into a matrix, into coordinates, right? So the neat thing here is that this is also constant memory, right? But it can actually quadratically increase the number of values to store. So there is some potential here for building these really huge sets, right? So we have a representation of finite sequences. And as I said on one of the first slides, our partitioning is just a sequence of finite sequences. So we drop all the fancy stuff now and just use lists for the infinite sequence here. And first, I will lift all the operations that I showed you on the finite sequences to these infinite partitions in a way that respects this understanding that each of these parts represent values of a certain size. So for simplicity, we use infinite lists everywhere here. In the paper, you can see how we deal more graciously with finite enumerations. So this gives the following short definitions for three of the 5 basic enumerations, right? Empty, singleton, and map. Nothing difficult here, am I right? Okay, and for sum, well, it's just a sip of the finite sum of the parts of its operands. Because of, I mean, the number of value in the nth part of this sum is of course the sum of nth part in the operand. So it gets lazy here, of course. We can't really give an upper bound on memory usage anymore, but this is sort of linear in the size of the largest element we fetch from this, or something like that. Right? So the number of parts that we actually evaluate, because these operations constant memory. Yeah, so before we define product, we need to, it helps to consider how we know that each part of a product is finite. And one answer is that there's a finite number of ways to divide size between the components of a pair. And each such division of size is just a finite product. So either we put 0 constructors in the first component and n in the second, or 1 in the first, etc. And if we just sum all this up, we get all the pairs of this size, right? So in Haskell, I guess that's a concatenation or a zip on the finite product operator. So this is kind of a convolution sum, you could call this, of the initial parts of the operands. Okay. And then the definition of product, we need to make this efficient somehow. I mean, computing the reversals. What we do here is we have a help function, reversals, which computes all the reversals on a list, and it does so using only linear memory. And then we define a convolution function which assumes that its second argument is already reversed. And then we can define product as just a map of the convolution of the left operand onto the reversals of the second operand. There's only a slight simplification here in the definition of con, which is, so in the actual implementation we carefully make sure that this one only holds on to x's and y's, so none of the kind of intermediate products that we create here. And when we do this, we get the same memory complexity as we had for sum, meaning kind of linear in the sizes that we're working with. Okay, so this is the most complicated slide. It gets easier for me. So now we have all the operators that we had for finite sequences, but this also means that we can still only build finite sequences. So we've made very limited progress thus far. But we actually only need one more operator to kind of complete this algebra and get everything that I said that we wanted to have on the first slide. I call this operator pay because what it does is increase the cost of all values in the enumeration, where cost is just a generalization of size. So the cost of a value is just, its index in this list of parts. And usually we want the cost to be the number of constructors in a value, but this pay operator gives us a slightly more fine-grained control of how we define cost. More importantly, pay is what I call a guarded recursion operator. And this means that it will kind of automatically deal with recursion for us, which is a very important part of making these automatical definitions. So I'll show you what this means in a second with some examples, but so what we can say is that if we have a cyclic definition of an enumeration and the cycle contains a pay, then we are guaranteed that all parts in the enumeration are finite. So, yeah, examples, starting small, enumerating booleans. Of course, booleans are just false plus true, and as can be expected, there are exactly 2 booleans, and they cost exactly 1. So this is kind of all the cardinalities of the first parts of this enumeration. So we don't need to have the pay here. If we removed it, it would just move this 2 to the first position, right? And then booleans will be free, cost nothing. A slightly more interesting example. So note that the enumeration here of natural numbers, it just mirrors the data type definition, as we kind of wanted it to do. A natural number is either 0 or it's s applied to a natural number. And we get the expected cardinalities directly because of what the pay operator does, right? So removing pay here would not be safe because that would put all the natural numbers in the same part, and that part will not be fine, obviously. So the example from the first slide. So yeah, lists also very simple definition, right? We add it's either empty or we apply the const constructor to a pair of booleans and list of booleans, and we get the same cardinalities we see here, where we have this every second part is empty. And this pattern of just putting pay on the sum of the constructors, which are defined by products of the constructor fields, it scales all the way up to huge systems of the types, like the Haskell syntax tree. So, yeah, that's about the definition of them. I would like to quickly say something about how we define kind of consumers of these enumerations. So the index function that we started with, this is a non-overloaded version of it, which takes an enumeration as an argument. So as I said on the second slide or something, it's just, so we get this flat enumeration by just concatenating all the partition, right? So that's just what we do here, and then we index it to it. Any objections to this?
Too slow. Too slow.
No, it's very fast. I mean, I can do the example on the first slide of this one. No problem. The problem is, I mean, I make so this is an infinite list, and I finitely concatenate it, right? So how does that work? Well, so if we consider the isomorphism of lists again, I only do index here, right? And I couldn't compute the length of this finite, just as I couldn't compute the length of an infinite list, but I can actually index into it, so it's kind of neat. But yeah, it relies on the fact that sum does not evaluate the cardinality of its second argument, so maybe it's a bit of a hack. Okay, yeah, we can also do random selection. So this creates a quick check generator given a finite set. Simple, of course. We just choose an index, which is in God, and then we pick out the value. And then we can lift this to a uniform generator over kind of an initial subset of the sequence by just choosing how many sizes do we want to include, just concatenate them, and we get a finite set from which we can randomly select values. So summing up our contributions, we have this nice algebra of efficiently computable functional enumerations. And it's simple enough to fit the code of my slides. And maybe more importantly, we have used this to actually find bugs. Now well, yeah, so I'm not as nice as Johan was, and I actually sort of divulge where we found the bugs here, but sorry about that. So our library is especially suitable for these kind of AST types, I would say, that are huge and have hundreds of constructors. And it turns out that these kind of types are very difficult to handle and test with in existing tools, like small-check and quick-check. You can read the paper to find out why. It's because of this size. I mean, it's, yeah. okay, finally, I would just encourage you to try it out yourselves. There's actually decent documentation on the Haskell page, and as I said, we have a template Haskell script that does the boilerplate.